All right, good afternoon, everyone, and welcome to the NEUTC Webinar Series. NEUTC, for those of you who are not familiar, is the New England University Transportation Center. We are a consortium of 7 universities, Norwich, Bunker Hill Community College, Holyoke Community College, UConn, MIT, New Hampshire, and then us here at UMass Amherst. And our UTC focuses on improving safety. Our presenter today is Professor Fei Miao from the University of Connecticut. Her work, which she'll describe here shortly, is on 5G-enabled safe and robust deep multi-agent reinforcement learning framework for connected and autonomous vehicle coordination. Quick primer on Zoom webinar. So you can use the chat feature for questions if you'd like, but there's also a Q&A section at the bottom. So as you come up with questions throughout the presentation, go ahead and drop them in the Q&A and we'll get to them at the end. And then if you do have questions or problems with Zoom, you can chat with the hosts via the chat feature. So I will pass it over to you, Professor Miao.
Yeah, thank you for the introduction, and I'm happy to introduce our group of work supported by NEUTC today. We have seen a lot of opportunities with the development of AI and embodied AI technologies. For example, we have seen better and better real-time predictions with a large amount of data based on deep neural network, and deep reinforcement learning also provides us a lot of possibility for better actions for our systems. And examples include like the AlphaGo game and AlphaFold, and also autonomous vehicles, drones, and manufacturing policies, etc. And specifically, our group is interested in multi-agent learning and control with communication capabilities in this big umbrella. And the main motivation is when we have more and more AI systems in our real-world life, collectively, their learning will be more efficient and bring more growth. To reach that objective, we actually still have a lot of challenges. So the first part is about safety. So if we just play video game and train our agent in simulators, we fail, that's fine, we just restart the game. But if it's real physical dynamic system, no matter it's a robot or it's autonomous vehicle, then the cost of failure is high, and also it can be even dangerous to human life. And another challenge is about how agents can coordinate to make the entire system efficient. With only one autonomous vehicle driving on this road, and perhaps it's okay, and to just drive as aggressive behavior. But when we have many autonomous vehicles and also human drivers, then we have to consider, okay, how these agents can better coordinate with each other, at least be like a good driver behavior on streets, right? So with that challenges in consideration, I think in today's talk, we would like to mainly cover 2 parts. So we will use these connected and autonomous vehicle framework as an example, and to explain when we have multi-agents in our system, from the perception part, how we can understand the perception model and specifically quantify the uncertainty of perception, and then utilize that part of knowledge to make robust and safe decisions, even under state uncertainties for a multi-agent system. So why we care about uncertainty in computer vision? So computer vision actually has, I would say, a very successful literature in machine learning fields in general for decades. And one example here, we just show object detection. What a computer vision can do is basically given cameras of images, and then machine learning model will tell a bounding box, like shown in this picture as a red box, as say, okay, this is a position of an object. However, thinking about this kind of situation, if the ground truth is red, but if the ground truth is green, but model's prediction is red, and then we just use the model prediction, the red box, to do path planning, then it is possible we plan an unsafe path for an autonomous vehicle. Instead, um, uh, just using this red box, we propose the method of quantifying the uncertainty of the vertex of the bounding box. Say, I would also like to estimate and predict the orange ellipsoid as covariance of the bounding box vertex. And then we can use the larger gray box as the object detection result and plan a safe path. So this becomes our motivation to better understand what can be the uncertainty of a perception model. And actually, we propose the first uncertainty quantification method for collaborative perception. Collaborative perception means these autonomous vehicles, they can share their vision-related information. And our method include both learning-based part to estimate what is the covariance matrix using data input. And meanwhile, in the training process, we also run statistics-based calibration, for example, like bootstrap method to better like calibrate our uncertainty estimation results. And then during inference stage, we basically can run like 20 frames per second of speed of both the prediction about the object detection result and also the uncertainty. And what we can reach is basically shown in this kind of video. It shows a bird eye view of autonomous vehicle's vision, and every vehicle has, for example, shared vision information from surrounding objects, from surrounding agents. Like here, we show the table, like each column is one type of vision information sharing method, and low bound means there's no sharing, and disconnect is one literature algorithm that shares intermediate features, and upper bound is one literature method that shares raw point cloud data. Basically, that's a lot of data, of course, heavy communication burden. But we want to understand, with all these methods, what about the accuracy and what about the uncertainty of the object detection result? And basically, the video is showing 20 frames per second of frequency, object detection, and also uncertainty quantification, where the orange ellipsoid basically represents the uncertainty. When we see a large orange ellipsoid, it means this estimation result, the machine learning model is not quite sure about it, the uncertainty is higher. And we basically compare our uncertainty quantification method with several literature, and the last row is our method. And we want to understand if we care about the uncertainty of the model, and if we have information sharing on the vision part, first, how can we improve the accuracy? And then second, what about the uncertainty? And it turns out that when we specifically put uncertainty reduction in the training process, we can reach the objective of both increase accuracy and reduce uncertainty when we have shared information among agents. So basically, this provides us some metric to evaluate the value of communication among autonomous vehicles. On the computer vision side, it can help to improve accuracy and reduce uncertainty at the same time, which is nice. Based upon this work with object detection, we've also studied what can happen for object tracking, and then it turns out if we input the object detection uncertainty as some additional information for tracking algorithm, then it can help machine learning model to improve object tracking accuracy, especially for those like missing detection objects compared with literature. And also trajectory prediction is one important and challenging topic for autonomous vehicles. And we again designed uncertainty reduction and uncertainty quantification method for trajectory tasks, considering there can be distribution shift during different time steps. And the basic idea is we utilize a tool called conformal prediction. And basically, if we compare our prediction in previous time step with like the real position of the surrounding objects we observe at the current time step, we figured out our prediction was bad. Then we enlarge the uncertainty set. And if it's like a good prediction, then we can shrink the uncertainty set range. So that's the basic idea. So here we want to show how we can utilize uncertainty information from 2D camera to 3D understanding, so which is called 3D semantic occupancy prediction. And the key idea is when we care about uncertainty, especially for safety critical classes like human and bicycles, we can significantly improve the object detection accuracy. Even in the data set, we actually only have a very small, like a maybe below 10% of examples that include humans, bicycles, motorcycles, etc. With all these, with some of these like computer vision tasks, I think here we mainly want to emphasize that first, when we have communication, then actually starting from the computer vision tasks, this can be useful for autonomous vehicles to improve vision accuracy and reduce uncertainty. And second, on different types of computer vision tasks, when we specifically put reducing uncertainty as an objective together with improved accuracy, that indeed can help the model to predict the result with better accuracy and smaller uncertainty. And quite often that can be related to especially safety critical classes identification. And then the question is, with vision information, how we can utilize that part information on decision making of driving, like should I keep lane or change lane? And then especially we want to put it in a complicated traffic scenario. Some are autonomous vehicles, some are not. And the question here is, in a situation where the object detection, trajectory prediction of the other vehicles are pretty accurate, then I think autonomous vehicle is in a pretty good stage, and we have a rich literature of path planning or control algorithm that can make sure our system plans a safe path and has safety guarantees. However, the challenging part is always say, what if computer vision cannot provide 100% accurate result, and what we can do? And nowadays, for decision making, deep reinforcement learning is pretty popular, and it has been validated as a useful approach for autonomous vehicles and also for many other types of robots. So the question we ask here is, if we consider there is state uncertainty, where state uncertainty is used to represent the uncertainty inherited from the computer vision part of models, then how we can define the problem and whether we have good performance guarantees. And it turns out that we can basically define the problem as multi-agent reinforcement learning problems and state uncertainties. And multi-agent reinforcement learning, if you have ever heard the word of reinforcement learning, we can consider it as game theory plus reinforcement learning. And the meaning is we put these multiple agents in one environment. We can consider, oh, this is one simulator or one like a driving map. So every agent can observe its own state, and it will explore what actions to take and take the action. And then the common environment can give feedback to every agent, say, basically represented as a reward function to tell the agent whether this is a good action or bad action. This part is very similar to the concept of reinforcement learning. The challenging part is, so first, we actually do not know the ground truth state transition function. And the state transition is governed by the joint state and action of all the agents. So it's like not one single agent can control the state transition. Second, the reward function is actually also related to the joint state and action of all the agents. Means as one agent, I can decide my own action, but actually I cannot control what others do, right? But the reward would also be affected by the other's action. These two factors make the entire process has the game theory flavor. So it becomes also tricky for us when we want to train some agents, how we define the reward function, how we define the game. Is it a cooperative game, a competitive game, a mixed game, etc. So that's also the interesting part. And of course, for this kind of multi-agent RL problem, researchers have designed a lot of algorithms, and one very popular architecture is what is called centralized training, decentralized execution. Means in the training stage, we can have some centralized knowledge for every agent. Quite often, it can be a centralized queue function, and then basically gives the agent some knowledge about at this time step, if I take this specific action, sort of others take different combinations of actions and what kind of reward I can get, utilize that part of knowledge to train its own policy. And during the execution stage, it's more like every agent is basically taking its own action. So no need to worry about what others are doing because it already gets that kind of experience during the training stage. And we checked the literature, we figured out that when there's no uncertainty, a lot of algorithm, but once there is state uncertainty for this multi-agent RL scenario, not too much work. So we first make some theoretical foundations to define what kind of equilibrium these agents are playing and figure out that under specific conditions, the game can converge. But for most cases, because there is state uncertainty, so actually, if the agent does not really have much knowledge about what is exact uncertainty and or if there is even adversarial in the process want to basically perturb the game, it's actually hard for agents to really calculate an equilibrium policy compared with normal MARL policies. So then we define basically the problem as a max-min problem, sort of robust optimization flavor, and define the solution concept and algorithm. And in simple environment like just the particle agents, we can train the policy of the every agents and to show basically robust MARL algorithm is better than non-robust MARL algorithm when there is indeed state uncertainties for the agents. And then the question would be how we can utilize our understanding on the theory part to deal with these real-world autonomous vehicle or robust scenario. So the situation here is, of course, similar to those kind of abstract theoretical model, we need to consider state uncertainty, and basically that will perturb our equilibrium policy solution framework. And then the second challenge is safety is still an important problem. So consider these two figures. So if our autonomous vehicle, which shows as the green cars, and its vision or state understanding is perturbed. If it still drives aggressively, then it is possible, say, because the understanding about the red vehicle's position is wrong, and if the green car still use this perturbed position as its ground truth knowledge, then basically the green car can plan a path where caused some accident. So aggressive, not considering for example, other vehicles' position can be perturbed or can have error, that can be wrong and can be unsafe. Another kind of situation is so our vehicles, the green cars consider there can be errors for the position prediction of surrounding vehicles, and then I am a little bit conservative and just want to keep 100% safety. Then extreme case can be, say, they just stop, right? Not going anywhere and not really reaching the goal point or destinations we plan for. So either solution is not good enough. And basically, we have to consider the trade-off between um, guaranteeing the safety of the system and state uncertainties, and also how we can still make sure the efficiency makes sense and these cars they can drive and they can reach the destination. So this kind of trade-off makes the problem much more challenging than like just caring about robustness or just caring about efficiency of the system. Regarding that, and we design multi-agent RL framework as this kind of architecture where the MERL is responsible for discrete action planning, like changing lane, keeping lane, or changing lane in within this speed range. Basically, that's discretized action space where we also have a high frequency, like low-level controllers to execute those kind of actions. Like controllers can finish the maneuver of changing lane within like 2 seconds, for example. And then the RL part has a framework where we follow the convention of actor-critic algorithm. And the robustness is taken by an algorithm, what we call worst case Q algorithm. Basically, when we calculating the Q function, instead of only maximizing the Q compared to classical MLRL algorithm, we define it as a min-max problem. It's like a maximum problem. Basically, maximize the worst case Q value. And of course, we have detailed algorithm on how we design this worst case queue to mimic the scenario where state information can be wrong and it's a perturbation for the MARL algorithm. So this is RL part. And meanwhile, we want the RL to get feedback information from the lower level controller. So basically, we leverage a control theory based technique called control barrier function. So we have an MPC CBF controller. The idea is for every action planned by the RL algorithm, the controller will check whether there exists a safe control input to finish the changing lane maneuver. If there exists, that's good, and it can utilize the controller to finish the maneuver. If the action is unsafe, it will also give a feedback and provide a negative reward to the RL part, basically let the agent know under this state, you cannot do this changing lane action, it's unsafe. And through the both training and testing process, we have this CBF controller together with our RL part to make sure that our agents can basically take safe actions and meanwhile also doing finishing its tasks like driving in front, driving to the front destination at somewhere, etc. Instead of say, oh, just stop there to guaranteeing safety. And here we first show the performance of the algorithm in simulations, where the simulator is called Color. It's basically open source online, and we can set up a different map and a different number of agents in these environments. And we, for example, train our agents in this sort of intersection scenario and also the highway scenarios. And for each scenario, we put different types of errors or perturbations to the surrounding vehicle states. And basically, the red vehicles are like an environment vehicle, and the green vehicles are autonomous vehicle where they basically coordinate with each other and controlled by our algorithm. And we compare our method with several baseline, including just a normal MARL, not too much safety requirements, or say with safety barrier function, but not the robustness part, or classical control-based method. And it turns out that our method shows at the upper line, it can reach, at least in these scenarios we train, it can reach 100% safety guarantee. And also overall, the efficiency is usually the best. Efficiency here, we basically use average speed of all the vehicles as a score. And on the simulator, it performs well. Then the question is, what about the hardware, right? And basically, it puts the problem to a higher level of complexity, where, of course, there can be simulation to reality gap, and we can clearly see this is our lab environment. It's quite different from what the color map show. And also, we can set up different agent numbers, and those stopping cars mimic like obstacles. And here we have basically not moving obstacle, and we also have scenarios where there are moving obstacles and complicated obstacles on like a different lanes. And my PhD students is also like, oh, changing the positions of the obstacles and see whether these two cars can still smoothly pass and smoothly change lane. And so there is simulation to reality gap, and we are using sort of different testing scenarios compared with what we have in the training. And also there is, for example, communication part can have communication delay on hardware. And we found out that if we just assume all the autonomous vehicles, they receive shared state information from a coordination agent in real time without any delay. If we train it that way and then directly deploy that kind of train policy from simulator to hardware, then the performance is not really good, because in reality, even in a lab setting, we can have communication delay. But if we simulate some sort of delay, even it's like just randomly generated some delay, and during the simulation process, and the agent is trained as, okay, occasionally it can have delay when it has delay from communication, and basically it just use its own local observation information as its state information to make the decision. If it's trained with that sort of like a delay aware communication protocol, then when we put it on hardware, the performance is much, I would say, is much more robust. So I think the idea here is, so first, when we have the control barrier function at safety shield, it definitely helps to transfer the policy from simulator to hardware, and the robust MRL policy also performs well when we do almost this kind of like a zero shot transfer. And of course, as we mentioned, we need to simulate or mimic communication delay through the training process in simulator. Then it helps to smoothly transfer the policy on hardware. And this is, I think we have already put this work on archive, but actually we are still adding more like experimental scenarios, and hopefully later we can also open source the code we put in simulator and hardware. And these hardware, basically it's F110th vehicle. I think it's pretty popular among many universities. Hardware part, it's mostly standard, but on the algorithm part, we indeed need to design a framework considering the safety requirements considering we want to make sure even under different scenarios, different agent numbers, these policies can be robust and also considering real world challenge, especially like a communication delay. And we also compare our policy with literature popular policy like a domain randomization. And for people who trained reinforcement learning policies for robots, domain randomization is pretty popular. And we figured out that if when we consider safety and robustness policies, that's better than those sort of just a randomly perturbed parameter style of domain randomization. It can save us training effort, save us training time. Yeah, I think we can skip our work on like the LM part. Actually, recently we are also testing VLA on cars, and hopefully later we can also share our work on say when each vehicle has those large language models and under complicated scenarios, whether they can have better coordinations, etc. Yeah, so here I put my past students and current students, and also some collaborators beyond the support from NEUTC. Yeah, so I think that's all my presentation and happy to answer questions.
All right. So thank you so much. Great presentation. So to our attendees, if you have questions, go ahead and drop them in the Q&A section at the bottom of your screen. I do have one kind of just to get the discussion going. So in one of your earlier slides on training the model, I think there was bikes and peds were very rarely seen. Is that correct?
Yes, for the
Is
second part. So that was from I think it's open source, like real world data. Yeah.
yeah. So I guess how do you balance between false positives or near misses? Like you talked about training the model to be either aggressive or conservative. Are there cases where you may trend towards being more conservative, or it's more beneficial to be aggressive?
Yeah, I would say that's indeed a pretty tricky part when we want to train some policy that's useful in real world. So theoretical analysis, there's some result, and basically, in algorithm design, it's just how we have some like a worst case Q function, and there is a weight parameter. Basically, that's a hyperparameter we can adjust, and when this part, the weight is high, then basically the model is more conservative, and the weight is low, the model is more like aggressive. Um, but if we say how we can connect this part with real world data. Um, I don't think I can give a pretty sort of like a rigorous or theoretical guaranteed answer. It's more like a um, other hyperparameter tuning, and basically we train the model and testing it with some like a challenging scenario. If it performs well and we feel okay, so the conservative level is already good. If we see a lot of errors, then a lot of like crashes or accidents in the training process, then we want to increase its conservative level a little bit. Yeah. So like in the training stage, we indeed tune that sort of parameter, and at early stages, we can still see like these the first number shows the number of crashes or number of accidents, for example. In early stages, it's not like just a zero, and for that scenario, we'll basically increase the conservative level of the model. Yeah.
And then is there a scenario where you have one parameter in certain situations and then another parameter in other situations? Like maybe you're more conservative when in the presence of, bikes and pedestrians than you would be not in that presence.
I think for these models training process, we don't specifically put humans or bicycles in these scenarios. We only use like um kind of a crazy drivers or even like people say run in the red, that sort of scenarios to train our autonomous vehicles. Um So I would say when if on the vision side we can successfully detect there is some human or bicycles, then basically that's an obstacle, and we just avoid the collision with obstacle as similar as avoid collision with other driving cars. So that part of algorithm is similar. The main challenge is still on the vision part, whether we can successfully detect it, even its rare cases in our real world data set. So I'm not exactly sure about current real world data set, but I know we also collaborate with like NVIDIA and Qualcomm. So at least in simulator now we can create a lot of like a synthetic data, and when there is human, there's bicycles, and then help the deep learning model to better identify or detect humans or bicycles. That's indeed help on improving the accuracy of the computer vision part. Yeah.
Great. And then I guess last one for me. I think you mentioned this, but what was the simulation software that's on this slide? Super
Oh,
cool.
so this is Carla,
Carla.
Cara, Calar.
Okay.
Yeah. It's pretty widely applied simulator, but I feel it's actually this is pretty early. I think around 2017 or sometime we already started to use color. But recent years, I would say there are several better tools according to what is your like a simulation needs. So, for example, if you want to focus more on, say, I want to put many around 10 agents in the simulator, and still I want the simulator to run pretty fast. The training process can generate a lot of different scenarios. If that is the case, I may recommend the Meta Drive. And we say our focus is on um, a very like a rich computer vision information, and I want the vehicle to do end-to-end understanding of the real world. If that is the case, then perhaps we just go to the large world models or the open source simulators from NVIDIA like ISAC-Sim, ISAC-Jim, and they are also like easier to use than Color.
Gotcha. Yeah, I mean, it looks just fun to play with. So, all right. I'm not seeing any other questions, so we'll go ahead and wrap it up there. Thank you for the great presentation, and thank you to all the attendees for joining today. If you missed something and want to come back to it, we'll be posting this on our website shortly. So it's neutc.org. And then keep an eye on your emails for an announcement for our NEUTC webinar next month. So thank you again, Dr. Miao.
Thank you.